Okay, everyone joined, sir. Shall we continue?
Yes, sir. We shall start, sir.
So yesterday we were discussing about alkanes, and we discussed about the preparation of alkanes in the last class, and also started with physical properties of alkanes. Now, the physical properties, we discussed the state in which this alkanes are existing up to four carbon atom gases, 5 to 17 carbon atoms, liquids, like that we have seen. Boiling point, I explained how it depends on mainly three factors. One is molar mass, another is size, and another is intermolecular attraction. So another physical characteristics is solubility. So if I want to dissolve alkanes in some solvent, what kind of solvent I can dissolve it, what kind of solvent it is not soluble. So that is what we are going to discuss here. So alkanes are non-polar in nature. So alkanes are non-polar because the electronegativity difference between the carbon and hydrogen, I explained yesterday, carbon-carbon electronegativity difference and carbon-hydrogen electronegativity difference is also very less. Therefore, there is no polarity developed in the molecule. So, as a result, they are considered to be non-polar in nature. And we must see that any solute, if you want to dissolve in a particular solvent, the nature of the solvent also must be similar. Like dissolves like, we say. So like natured solute can be dissolved in like natured solvent. So like dissolves like. So here we have non-polar nature of the alkane. So these alkanes we can dissolve in non-polar solvents. But say water is a polar solvent. Water is a polar solvent. That means alkanes you can't dissolve in water. They are insoluble in water, but they are completely soluble in organic solvents. Organic solvents are non-polar in nature. So alkanes are insoluble in water because water is a polar solvent, whereas alkanes are non-polar. Like dissolves like. That point you must remember here. So based on that, we can say alkanes are insoluble in water. And organic solvents, since they are non-polar in nature, so alkanes can be dissolved in non-polar solvents like organic. We can say ethers. We can consider benzene, carbon tetrachloride. All these are organic solvents. So alkanes can be dissolved in such organic solvents. So that is the solubility. Now what happens as the molecular mass increases? So as the molecular mass increases, you can observe that the solubility goes on decreasing. So for example, grease, it is a mixture of higher hydrocarbons, is soluble in petrol. So it is, you can dissolve that in petrol. Grease is one of the examples you can take. As the molecular weight increases, solubility decreases. Petrol and lower fractions of petroleum are generally used for dry cleaning. So we already know one of the important application of this petrol is petrol and their lower fractions, means lower number of petrol is a long chain hydrocarbon. So lower fractions of petroleum means the lesser number of carbon atoms. Those are particular compounds. We can say those are used especially in dry cleaning because of this. This is one of the applications of this hydrocarbons as with respect to their solubility. Now coming to very important part, chemical properties. As we already know, alkanes are completely saturated. So saturated hydrocarbons are very little affinity for any oxidizing agent, reducing agent, or any of oxidizing agent, reducing agent, or acids, bases, they are not going to react with. But under normal conditions, it all happens. If you take the drastic conditions, high temperature condition, diffused sunlight condition, or temperature conditions, heat, if you heat them under high temperature, so we can see some of the chemical properties of these alkanes. Out of the different chemical properties, some chemical properties I can just discuss here with respect to this substitution reaction. So substitution means what? All of you must know what is substitution. So substitution means, let us take here, we have a compound like AB. Now, if I react with some X, this one. Now, in this, one of the atom or group, B may be an atom or group. So this atom or group is replaced by X. The product what we may get here is X plus B. So this is called as substitution. One atom or group is replaced by another atom or group. That is generally called as substitution reaction. So alkanes, we have carbon-hydrogen bond, right? So this is carbon-hydrogen bond. We can have like this, hydrogens attached here. And in alkanes, one or more hydrogens we can replace with, say, halogen we can replace it with. We can replace it with nitro group. Nitro group is NO2 group. We can replace it with sulfonic acid group. Sulfonic acid means SO3H group. But we can replace it only under certain conditions, that is high temperature condition or in the presence of light, and these reactions we can call them as substitution. One or more hydrogens of an alkane which can be replaced with halogens, nitro group or sulfonic acid group, we call them as such reaction as substitution, but this reaction can be carried out at very high temperature or in the presence of light. So this is called as substitution reaction. So let me take few example here, very important examples. We call halogenation. Only this is the reaction you have for NCERT syllabus. Halogenation of alkanes. Halogenation means, you know, halogen is the 17th group element. It is the substitution of halogen in place of hydrogen. So that is nothing but halogenation. Substitution, one or more hydrogen are removed, and in place of those hydrogens, we are just adding what? Halogens. So such reaction is called halogenation, and it can be done at very high temperature range between 573 to 773 Kelvin, or you can carry out this reaction in the presence of diffused sunlight. So I will take one example of chlorination of methane. So chlorination of methane in presence of sunlight, if you take limited quantity of Cl2, or say 1 mole of Cl2, if you take, now you can replace one of the hydrogen from CH4, methane, and it can be replaced with the Cl, and you will get the CH3Cl, because one hydrogen has been removed from methane and it is been replaced with Cl. And byproduct what we are getting is HCl, because here we have Cl bond. Here we have one of the hydrogen is combining with this Cl, one hydrogen is combining with Cl, and it goes as HCl, and remaining three hydrogens as it is, CH3Cl. We call it as chloromethane. Now, if we take this chlorine in excess quantity, so we can replace more than one hydrogen also successively. Say if I take CH3Cl, one more mole of chlorine if I take, I can replace one more hydrogen like this, and it becomes dichloromethane in this case. So chloromethane becomes dichloromethane, one more mole of chlorine if I react it with. Similarly, dichloromethane can further be substituted with one more chlorine atom. We can get chloroform, that is trichloromethane. So Trichloromethane can further be converted into carbon tetrachloride or tetrachloromethane with excess of Cl2 if we add. So successive replacement, successive substitution of methane will end up with last product as carbon tetrachloride when you replace all the hydrogens of methane with chlorine. So this is called carbon tetrachloride successive substitution of methane. So the entire process we can call it as chlorination of methane. So this is chlorination of methane. Another example we can take, like say if we have ethane, chlorination of ethane in presence of sunlight, you can replace one of the hydrogens from ethane, you can get chloroethane. So plus HCl, like that you can get. But the important point to be understood here is the mechanism. When I do mono substitution, what do you mean by mono substitution? Means only one hydrogen is replaced with the Cl. Monohalogenation. I'm not successive halogenation, I'm not doing monohalogenation. If I do, what is the mechanism it follows? So we say it is following free radical mechanism. We say that it is following free radical mechanism. What do you mean by free radical? First chapter you must have come across about free radicals. So free radicals are the species of the intermediates obtained when the molecule undergoes homolytic cleavage. I hope you remember this. So homolytic cleavage, say if A, B, there is a covalent bond between them, there is a sharing of electron. If I want to break this bond homolytically, generally homolytic cleavage takes place either at high temperatures or in the presence of sunlight. So one electron goes to this atom and another electron goes to this atom, and this bond is going to break. This is called as homolytic fission, homolytic cleavage. As a result of that, this A will get one dot, which is called unpaired electron over here, and B also has an unpaired electron. So both A and B having an unpaired electron means the electrons which are not involved in bonding but single electrons. These are called as free radicals. So free radicals are the intermediates, reaction intermediates formed due to the homolytic cleavage of the covalent bond. So here the chain reaction, so mechanism is a chain reaction here. The chain reaction of chlorination of methane starts with this particular homolytic cleavage. This is called as chain initiation. Homolysis of chlorine molecule. So like this. So chlorine molecule undergoes homolytic cleavage. So here we have two electrons. It will undergo homolytic cleavage. One electron goes here, another electron goes here. Now the question arises, we are doing this reaction actually, methane plus Cl2, it is giving you CH3Cl plus HCl. This is the reaction. Now here there are different bonds are also cleaved. Here CH bond is also cleaved, right? Cl bond is also cleaved. So now the question arises, why CH bond is not undergoing homolytic cleavage in preference to Cl2 bond? There are two possibilities. Cl2 can undergo homolytic cleavage, or CH can also undergo homolytic cleavage under the given temperature condition or light condition. Why not Cl only will undergo homolytic cleavage? The answer is very simple. As I told, bond length, yesterday we discussed this, bond length is less means bond strength is more. Smaller the atoms, more is the bond strength, because bond length will be less. The bond length between carbon and hydrogen is less. Therefore, cleavage of this is little difficult as compared to this, because chlorine atoms are larger, carbon and hydrogen atoms are smaller. The bond length between carbon and hydrogen is very less compared to Cl-Cl bond. Therefore, Cl-Cl bond undergoes homolytic cleavage in preference to CH bond, and if at all we have ethane or some more higher alkane, CC bond is also not cleaved in preference to Cl-Cl, because CC bond is also stronger than Cl-Cl bond. So hence we are going to get chlorine free radical on homolysis. This is the chain initiation step. the chain gets initiated by the homolytic cleavage of chlorine molecule. So we are getting chlorine free radicals over here. So chlorine free radicals. Now these chlorine, in the next step, once the chain gets initiated, it gets propagated. So chain propagation. So what happens, how the chain gets propagated is this chlorine free radical now induces the homolytic cleavage in methane molecule. Say methane has 4 hydrogen, carbon is attached with 4 hydrogens here. Now this chlorine free radical makes this bond undergo homolytic cleavage, and it will now undergo homolytic cleavage. We'll get H dot here and CH3 dot. This H dot, this is an unpaired electron. This Cl dot, this is an unpaired electron. Both will share these 2 electrons and form HCl, and followed by the free radical generated over here. And this is the free radical generated called as methyl free radical. So this is how the chain gets propagated. Then this methyl free radical again reacts with one more molecule of chlorine. So this is the chain reaction. It goes like this. The methyl free radical further reacts with chlorine molecule, just generating methyl chloride and chlorine free radical. So both A and B steps, the earlier step was A step and this step is B step. These two steps further go on repeating, and this will propagate the entire reaction in the formation of CH3Cl. Now once all the molecule have been completed their particular formation of CH3Cl, all the say if I take 1 mole of methane, if all 1 mole of methane gets completed with formation of CH3 free radical, then further chain gets terminated, because if there are any remaining Cl free radicals, CH3 free radicals or CH3Cl free radicals, they are going to combine further. So this is how the chain gets terminated once all the molecules of methane are completed with their cleavage of homolytic cleavage and formation of methyl free radical. Once that is done, then maximum amount of CH3Cl is going to be formed, and the remaining, if at all any free radicals are remaining, so those free radicals combine together. So these are the possible free radical combination. So you can get a little amount of ethane also as a byproduct over here. So byproduct, you're going to get ethane along with methyl chloride. A little amount of ethane is also obtained in this particular reaction. So this is called as chlorination of methane. Any doubt in this mechanism? Anyone has? No doubt. Shall we continue? Yes. The points to be noted here, very important points. Now, in the chlorination of methane, what kind of, we have learned yesterday, types of carbon atoms: primary, secondary, tertiary, and quaternary carbon atoms. You know, primary carbon atom has 3 hydrogens attached. Secondary carbon atom has 2 hydrogens attached. Tertiary carbon atom has 1 hydrogen attached to it. Whereas quaternary carbon atom does not have any hydrogens attached to it. So now, among primary, secondary, tertiary, which hydrogens can easily be replaced? Which can be replaced faster rate of replacement of hydrogen? So we call primary carbon, the hydrogens which are attached to primary carbon are called as primary hydrogens. The hydrogens which are attached to secondary carbon are called as secondary hydrogens, tertiary hydrogens. The order of replacement will be third degree, that is tertiary, secondary, primary. So why tertiary is more preferable over here? Because here the intermediate formed is free radical. So tertiary means you have only 1 hydrogen attached to this. This is tertiary carbon. Now if this is cleaved, now what we are going to get as an intermediate here is like this, 1 dot, and this is tertiary free radical. Now in the first chapter, you have come across the order of stabilities of free radical. Tertiary free radical is more stable than secondary free radical, is more stable than primary free radical. The product what we are going to obtain is based on the stabilities of the intermediates what we obtain. So stability of the intermediate, that is tertiary free radical, is more stable than secondary free radical, is more stable than primary free radical. So therefore, which hydrogen can easily be replaced is tertiary hydrogen can easily be replaced because the intermediate formed during this process is tertiary free radical, and in intermediate formed in this case is the secondary free radical. Intermediate formed in this case it is primary free radical. So that is how you need to understand this. The CET questions will be asked based on this. But if you take with respect to halogens, which halogen is highly reactive? Fluorine is highly reactive. Fluorine reacts actually violently. So therefore, we generally don't carry out fluorination. We generally carry out chlorination, bromination. Fluorination is violently reactive. Therefore, we don't carry out. Fluorination is too violent to be controlled. We can't control it so easily. And iodination is very slow and it is a reversible reaction. So if I want to do iodination reaction, so chlorination, bromination can be easily carried out. Fluorination, since it is highly reactive, can't be controlled. It is very difficult to carry out. But iodination is also not advisable because it is reversible in reaction. I'll just take this example here. If you want to say iodinate the methane to get methyl iodide, and the byproduct what we are getting here is HI. You can do this, but only in the presence of some oxidizing agents like HiO3 or HNO3. These two are oxidizing agents. So in the presence of oxidizing agent, you can carry out. Why in the presence of oxidizing agent only we can carry out? Because if you don't use the oxidizing agent, HI again can react back to CH3I. Then again you can get methane and iodine. Iodine being more stable here. So therefore, the reaction can be reversed. Therefore, what we have to do to make this reaction go only in this direction, I want to make this reaction to go. If I want to make this reaction to go only in this direction, I have to remove this HI. If I remove HI, then CH3I does not have any HI for reaction, and hence more reaction will go in this direction. And hence, how to remove this HI? So remove this HI by adding HiO3 or HNO3. So HiO3 and HNO3 will react with this, say, let us say HiO3. So will react with this and form iodine over here. So it is going to form iodine with this HI. HiO3 can react with HI and it forms iodine. In turn, iodine, whatever is formed, will help in increasing the concentration of iodine and making this reaction to go further into forward direction. Because here, if I increase the concentration of this, more of forward reaction takes place and iodine can be more liberated. CH3I can be liberated in the more concentration. So therefore, iodination we can carry out, but only in the presence of oxidizing agents. Now, I have one reaction here. Propane chlorination. What is the product? Can anyone tell me? Can anyone tell me? What is the product? Use only monochlorination. Only one hydrogen is replaced. Only one hydrogen is replaced. So what is the product we are going to get here? There are two possible products here. Say if you replace hydrogen from this carbon or this carbon, you will get one product. But if you replace hydrogen with this carbon, I'll get another product. Means here, if you replace any of these, you will get one chloropropane. If you replace with this, two chloropropane we get. Which is the major product in this case? The major product in this case will be 2-chloropropane, because just now I explained during the formation of 2-chloropropane, you will get the secondary free radical as an intermediate, and secondary free radical is more stable than primary free radical. Therefore, you are going to get the major product as 2-chloropropane rather than 1-chloropropane, which is a minor product. Both products you are going to get, no doubt in that, but the major product would be 2-chloropropane compared to 1-chloropropane. Any doubt in this? Yes. So next chemical property is combustion. So combustion reaction means burning process, burning in the presence of oxygen. Generally, all hydrocarbons, when burnt in presence of oxygen, they give completely, when you burn them in the excess of oxygen, you are going to get carbon dioxide and water as the product. So let us take this example. See, for butane, when you burn in presence of oxygen, carbon dioxide and water. So this is the general reaction I have given: CnH2n plus 2 plus 3n plus 1 by 2 O2, giving NCO2 plus n plus 1 H2O. So this is the combustion reaction, complete combustion. So complete combustion of hydrocarbons, especially alkanes, will give you carbon dioxide and water with enormous amount of heat liberated during the process. In the last class, I told heat liberated can be converted into mechanical energy. So we use these hydrocarbons as fuels. So if you do incomplete combustion, means limited supply of oxygen, if you have not, you are not taking excess of oxygen, you're taking only limited supply of oxygen. So these hydrocarbons, these alkanes burn incompletely. So when incomplete combustion is done, you can get carbon black. So this carbon black formed, we can use that in ink or black pigments or and filters. So this is the reaction called combustion reaction. So this is another important chemical property we have is controlled oxidation. So controlled oxidation using different catalysts, different products we get if we have same reactants also. See, for example, you can take this methane and in the presence of oxygen, if you heat it up to 523 Kelvin temperature, and in the presence of copper as a catalyst, maintaining the 100 atmospheric pressure. These are very important conditions. Important conditions you must remember. So what you are going to get as a product is methanol. So here we get the product as methanol or methyl alcohol. So conditions are copper, 523 Kelvin temperature, 100 atmospheric pressure. So this condition we can control this oxidation. The desired product for us is alcohol. I want methanol to prepare methanol, so I can use this. In this particular conditions I can use and get the methanol as the product. But if I use the same reactants I have, CH4 and O2, methane and oxygen, but I don't want methanol, I can't use the same reaction. I have to use some other catalyst over here. Catalysts are specific in nature. So a particular catalyst can catalyze and give some different products. So molybdenum oxide, if I use MO2O3 and heat it, we may get here methanal. It is not alcohol, it is aldehyde, commonly called as formaldehyde. So formaldehyde is obtained in this process. See, reactants are same, methane and oxygen, but the catalyst is different. And this catalyst help in getting formaldehyde, not methanol. You're not going to get methanol here, you're going to get methanal instead, and formaldehyde is going to be formed. So next, if I take ethane and do the controlled oxidation with manganese acetate, heat it, and you will get acetic acid also here. So this is another reaction, ethane on controlled oxidation with manganese acetate, acetic acid is obtained. So this is another example of controlled oxidation. So if I say generally we use for oxidation KMNO4H plus we use, or K2Cr2O7 in presence of acid, H plus in the sense acid. In the acidic solution of KMNO4, in the acidic solution of K2Cr2O7, these are called as strong oxidizing agents. We call them as strong oxidizing agents. Now, whether alkanes can be oxidized by KMNO4 or K2Cr2O7, acidified KMNO4 or acidified K2Cr2O7, the answer is no. So even with the strong oxidizing agents, we can't oxidize normal ethane, normal alkanes. But under one condition, we can oxidize. What is that condition? The condition is, see, we have like this. In this condition, you just observe what is the condition. This carbon is primary, this carbon is primary, this carbon is primary, no doubt. But this carbon is tertiary. And this is the hydrogen, which is called tertiary hydrogen. So the alkane containing tertiary hydrogen, it is possible to oxidize with respect to what? with in the presence of KMnO4H plus. We can use this condition which releases nascent oxygen, wherein this oxygen gets added over here. Addition of oxygen is nothing but oxidation. So we are going to get this alcohol, which is called as tertiary butyl alcohol as a common name, and IUPAC name is nothing but 2-methyl propane 2-ol. It will be something like this: CH3, CH3, CH3OH, 1, 2, 3. That is 2-methyl propane 2-ol, because alcoholic group is in the second position. So this is one more condition wherein we can make the oxidation if we have tertiary carbon and tertiary hydrogen. So the tertiary hydrogen, if we have in an alkane, it can be oxidized using acidified KMnO4 to get the tertiary alcohol. We call this type of alcohol as tertiary alcohol. So this is another example of. So now, can you tell me what is the oxidation product here in this case? So this is, here we have one hydrogen and this is tertiary carbon. You can see. So this is one tertiary carbon, and we can just add oxygen there. So this is the product we are going to get. 1-methyl cyclohexanol. The name of this compound is 1-methyl cyclohexanol as the product. So likewise, controlled oxidation. When tertiary carbon is there, the tertiary hydrogen can be oxidized by KMnO4H plus, giving you corresponding tertiary alcohols. Any doubt here? Next reaction is isomerization. So isomerization means what? Isomers means compounds having same molecular formula but different structural formula. So we can obtain the chain isomers of alkanes by this isomerization process. So how we can carry out chain isomerization is, we have to use this condition. And you have to remember this particular catalyst. So if I heat N alkanes means straight chain alkanes. N represents normal over here. Normal. So when you have normal alkane, in the sense there is no branching in that alkane. So the alkane is straight chain alkane. So here N hexane means CH3, CH2, CH2, CH2 4 times CH3. So N hexane, you can obtain the branched alkanes when you heat it in presence of AlCl3 or HCl gas, any one. So either you pass the vapors of N-hexane through anhydrous AlCl3, or the vapors are passed through dry HCl. So then you can just obtain the isomers of this N-hexane. These are chain isomers. What do you mean by chain isomers? The number of carbon atoms will differ. So here it is 2-methyl pentane and another is 3-methyl pentane. So chain isomers are obtained. This is called as isomerization. Molecular formula of 2-methyl pentane, 3-methyl pentane, N-hexane, all are same. But N-hexane is straight chain alkane, whereas 3-methyl and 2-methyl pentanes are branched chain alkanes. So this is called isomerization. You have to remember that particular catalyst, anhydrous AlCl3 or HCl. Aromatization. So aromatization means you can convert N alkanes into an aromatic compound. N alkane is converted into an aromatic compound. Let us say for us, aromatic compound means benzene. So we can convert this into benzene. So benzene has 6 carbon atoms, means let me take an example of 6. The one which has 6 carbon atoms, N-hexane only. N alkane means again straight chain alkane only we have to take. The conditions to be maintained, you must remember. Here we have to heat that N alkane up to 773 Kelvin. Vanadium pentoxide or Cr2O3 or MO2O3 or Al2O3 alumina. Any of these we have to pass the vapors of N-hexane, maintaining the temperature of that as 773 Kelvin. So then N alkane can be converted into benzene and its homologue. So what do you mean by that? I'll just tell you. Here, this is N-hexane. I can write it like that for our convenience. Instead of straight chain, I'm writing like this. This is a straight chain compound only. To understand what is the product we're obtaining, we have just taken like this. Any of these catalysts we use, and 773 Kelvin, it is been converting into like this, benzene. And the pressure to be maintained also, you must remember here, 10 to 20 atmospheric pressure. So now if instead of N-hexane, if I use N-heptane, let us take here CH2CH3. Like this, if I take, this is N-heptane. So if I use N-heptane, I'm getting here, see, these 6 carbon atoms will join like this, having alternate single or double bond. And this CH3 will be like this. And what is the name of this? This is toluene. So this is a homologue of benzene. This is the homologue of benzene. So this kind of aromatization also can be done. So N-heptane if I take, I'll get toluene. N-octane if I get, I will get CH2CH3, ethyl benzene. This is another homologue of benzene. Are you getting that point? The benzene and their homologue. So N-hexane will give benzene, N-heptane will give toluene, N-octane will give you ethyl benzene. So like that, we can obtain in this aromatization. The thing what you need to remember here is these conditions. These conditions are very, very important. Reaction with steam means water vapors. So if you react alkanes with water vapors, one of the reaction we take methane with the steam in presence of nickel as a catalyst. When you heat it, you will get carbon monoxide and hydrogen. So we call this mixture as water gas. The mixture of this is called as water gas. Another name is there called syngas. So water gas or synthesis gas, syngas we obtain. This is another chemical property of this alkanes. Alkanes react with steam at this temperature. Remember this, 1273 Kelvin in the presence of nickel catalyst give carbon monoxide and hydrogen. The mixture of carbon monoxide and hydrogen gas is called as water gas. So to prepare hydrogen, dihydrogen by industries, we use this water gas. Water gas can also be used for different preparation of organic compounds, like methanol can be prepared, methanal can be prepared if we use different catalysts. We can also prepare methanol, methanal by this water gas. Has very much applications. Water gas has very much application. Therefore, we call in short as synthesis gas. It is used in the synthesis of different types of organic compounds. So water gas. Last chemical property you can see here with respect to alkanes is pyrolysis. Pyro means heat. Lysis means breaking. So you are going to break the bond between the carbon atoms by heating, only by heating. So this is called pyrolysis. This reaction is called pyrolysis or cracking. Only by high temperature decompose to lower alkanes or alkenes. This also follows free radical mechanism over here. You can take this hexane. So hexane, when you heat it up to 773 Kelvin temperature, you may get different fragments here. This is called hexene. This is butene and ethane. Different possibility depending on how much bonds it is going to break. Ethane, here propene, it is C3H6 is propene, ethene and methane. So like that, it can be broken into different fragments and it is called pyrolysis, and this pyrolysis is done only by increasing the temperature or heating the compound alkene. So this is one of the chemical properties. Another example, dodecane C12H26. When you heat it up to 973 Kelvin temperature in the presence of platinum, palladium or nickel catalyst, you may get heptane or pentane and other byproducts you may get over here. So pyrolysis we mainly use to prepare petrol or kerosene from gasoline. So gasoline has a long chain hydrocarbons. So if I want to break it up to only 8 carbon, we generally call it as petrol octane. So octane means it is having 8 carbon atoms. If I want to break it, so I can use this pyrolysis process for getting that particular petrol or kerosene from gasoline. So this is another reaction what we have, last reaction. Any doubt in the chemical properties of alkanes? Shall we start with alkenes?
Yes, sir.
Yes, sir.
Okay. Yes, now alkenes. So you know alkenes, at least one carbon-carbon double bond should be there, and we call them as unsaturated hydrocarbons. They are not saturated because carbon has at least one double bond. So it is not completely saturated in the sense how this double bond is going to be formed in this alkenes. The structure we are going to discuss over there. And these are called as olefins because they have the ability to form oil forming. Olefin means oil forming ability. The compounds, these alkenes have oil forming ability. Therefore, they were called as olefins. And general formula, all of you know, CnH2n is the general formula where N is the number of carbon atoms. Now, if you look into the electronic structure of this particular ethene molecule, both carbon atoms, the doubly bonded carbon atoms here are sp2 hybridized. So you know sp2 hybridized orbitals, how many sp2 hybridized orbitals will be there? 3 sp2 hybridized orbital having trigonal planar geometry, all have 1 unpaired electrons. And another carbon also has sp2 hybridization, and it also has trigonal planar geometry. One of the sp2 will overlap with this sp2, and this is having one unpaired electron, this is having one unpaired electron, this is also sp2, this is also sp2, this is also sp2. All these are sp2 hybridized orbitals. Now these sp2 hybridized orbitals overlap with s orbital of hydrogen, here one s orbital of hydrogen, here one s orbital of hydrogen, here one s orbital of hydrogen. So it is going to overlap. Now you know carbon has one 2s1 and 2px1, 2py1, 2pz1. In the excited state, the configuration is like that. So 1s2, 2s1, 2px1, 2py1, 2pz1. Only two p orbitals are involved in hybridization. One of the p orbital has not involved in hybridization, and that this is the internuclear axis. That the p orbital which has not involved in hybridization will be unhybridized, will remain unhybridized, and also it has one unpaired electron. This carbon is also having one unhybridized orbital. This carbon also has one unhybridized orbitals having an unpaired electron. Therefore, these two will overlap laterally, forming pi bond. So these two will form pi bond. So therefore, one of the bond, which is pi bond, pi electron cloud will be above and below the plane. You can observe here, above the plane and below the plane. You can observe, not in between the plane. So the pi electron cloud will be above and below the plane over here. So therefore, you must, in this particular alkenes, you can consider them as electron rich species. They are electron rich in nature. So they are electron rich. So therefore, alkenes are electron rich species. They can easily give away their electron and they become saturated. Since they're unsaturated, they can easily become saturated by giving the pi electron cloud. So that is one of the important feature of this particular this one. The bond angle in sp2, you know, it is 120 degree. And what is the cc bond length? cc bond length in single bond length is 154 picometers. Yesterday we have seen, but double bond length is 134 picometers. It is decreased because double bond is shorter than single bond. So double bond is shorter than single bond. One more point, in single bond, we have CH bond length. So CH bond length is around 112. Yesterday we have seen 112 picometers. Single bond length. But double bond length between C and H is not exactly 112. It is less than 112. Because this carbon, sp2 hybridized carbon, is having more electronegativity than sp3 hybridized carbon atom, which is of very important character here. So therefore, CH bond length is slightly decreasing in alkenes compared to alkenes. The hydrogen which is bonded to sp2 carbon is having lesser bond length than the hydrogen which is bonded to sp3 carbon. That is another point to be understood in this. So 108 picometers, you can see here 108 picometers, but here we have 112 picometers. So this is another important feature we can have. Now let us take a simple classification of this alkene to understand the chemical properties of this alkene. See, if we have carbon-carbon double bond, and if we break this carbon-carbon double bond across this, if we get similar groups, CH3 this side, CH3 this side, the alkene in which similar groups are attached to this double bond, we can call such alkenes as symmetrical alkenes. And if we have different groups attached on either side of the double bond, then we can call it as unsymmetrical alkene. So if I break this bond, so it is not equal. So these are not equal, therefore we can call it as unsymmetrical alkene. Very important. You must know what is asymmetrical alkene, what is unsymmetrical alkene. Now, one more important feature of this alkenes is they exhibit geometrical isomerism. So what do you mean by this geometrical isomerism and why it arises in alkenes? Now, in alkanes, we have seen that there is a carbon-carbon single bond and the rotation around the carbon-carbon single bond is slightly free. We can easily rotate. This bond is not going to disturb. This carbon-carbon single bond does not get disturbed by the rotation of one of the carbon atoms between carbon-carbon single bond. But when we have carbon-carbon double bond like this, the rotation is restricted. You can't rotate. Here it is restricted. Someone asked, single bond is restricted to very small extent. But here in the double bond case, carbon-carbon double bond is having a restricted in their rotation. It is not complete. It is not free at all. Why? Because I just explained this pi bond is formed by the overlap of what? By the overlap of this unhybridized orbital, which is having the electron cloud above and below the plane. So when I rotate one of the carbon, this cloud, electron cloud, gets disturbed. The pi electron cloud gets disturbed. Therefore, it is not possible to rotate. But in case of single bond, it doesn't get disturbed much. The single bond doesn't get disturbed much, but here the double bond gets disturbed. So because of that reason, the relative arrangement of these groups or atoms attached here to this carbon-carbon double bond, say, let us say carbon-carbon double bond, we have some groups or atoms attached. So based on the groups or atoms attached over here, based on the groups or atoms are attached, we can have cis and trans isomers here. So there are two types of isomers we can take. The relative arrangement, that means spatial arrangement. So relative spatial arrangement of atoms or groups attached around carbon-carbon double bond, based on that, we can have geometrical isomerism. So you must listen very carefully under what condition we can see such type of geometrical isomerism. Say, let me take this particular group as A and this particular group as B here. Here it is A and here it is B. So now the geometrical isomerism arises only when A is not equal to B. Very, very important condition. A should not be equal to B. If A equal to B, then there is no geometrical isomerism. That means the doubly bonded carbon atom should not get attached to the same atoms or groups. Now, if I have something like this, here we have CH3, here we have CH3, here we have CH3, here we have H. Let me take like this. Now, this will not show any geometrical isomerism because here these two groups are same, even though these two groups are different. So this doubly bonded carbon atom, if it is attached to similar groups, then you can't have geometrical isomerism. Yes, this is one more very important condition to be understood. Now, if the condition satisfies, if A is not equal to B, A can be, if we can also have A, B, C, D, all different, that is, then also we can have cis and trans isomer or geometrical isomer. But the atoms or groups attached to the doubly bonded carbon atom should not be same. Now, in this, we have two types. In this geometrical isomerism, the spatial arrangement, we have two types. One is similar groups are attached on the same side like this. We call it as cis isomer, cis but 2-ene it is. And if similar groups are attached on opposite side like this, we call it as trans but-2-ene. So there are two types of geometrical isomerism. One is cis and another is trans. We can also call this isomerism as cis-trans isomerism. I hope you understood the conditions for this cis-trans isomerism. Any doubt here? Yes. So now let me take with respect to the IUPAC nomenclature. So ethene, it is ethyl common name. This is common name. IUPAC name is ethene for this. You can take 1, 2, 3. Double bond is functional group. It has to be given priority. Propylene is the common name for this. Propene is the IUPAC name. And here in this case, 1, 2, 3, 4. Alpha butylene is the common name for this. But-1-ene is the IUPAC name for this, or 1-butene. So it is 2-butene. This is 2-butene or but-2-ene. So this is the IUPAC name for this particular compound. So this is one example I have taken. Let me take few more examples. Now if I take like this is having 7 carbon atoms. If I choose this as the longest carbon chain, but actually this is not the longest carbon chain. This is the longest carbon chain. C2H5 can be written as CH2CH3. So now this becomes the longest carbon chain having 8 carbon atoms. Therefore, this is wrong. And hence this is correct one. So numbering, how we can do numbering here is from this here. 1, 2, 3 from right side, because double bond should be given more priority. Second position it will come. So 4-ethyl, 6-methyl, oct-2-ene is the IUPAC nomenclature for this. This is one of the examples of IUPAC nomenclature. So let me take another example here. This, how we can number is double bond has to be given priority here. This is the wrong way of numbering, even though it has a longest chain. So we have to consider the longest chain like this only, because double bond has to be given the priority, and pent-1-ene, 2-ethyl pent-1-ene is the IUPAC nomenclature for this. So double bond should be given the priority because it is a functional group for us in this. If I take this example, how I can number it, how I can choose the longest chain over here like this. You can see this is the longest chain possible. So oct-3-ene. So this is 1, 2, 3. How many methyl groups are attached in this? Third position, fourth position, and sixth position. 3, 4, 6. Trimethyl oct-3-ene is the IUPAC nomenclature for this particular compound. So IUPAC name. I have taken only few examples over here. So this is another example. I have to number it from here only. 1 has to be given for this. 1, this is the longest chain. 1, 2, 3, 4. Double bond is given priority. Oct-1-ene, and it is a bond line representation, means the terminal carbon will be CH3 methyl here. This is CH2CH3. This is ethyl group. So therefore, you can just take the IUPAC nomenclature as 4-ethyl 2, 3, 5 trimethyl oct-1-ene is the IUPAC nomenclature of this particular compound. Let me take another example over here. So 3-ethyl 2, 7 dimethyl tec-4-ene. IUPAC nomenclature is given. Based on that, if I want to write the structure of this, how I can represent the structure of this? Dec-4-ene means it has 10 carbon atoms. First represent the 10 carbon atoms like this. And fourth position, there is a double bond. So mention number from left to right or right to left anywhere, but fourth position, you have to keep the double bond. Then third position, you have to keep ethyl group. Second position and seventh position, you have to keep methyl group, and remaining everywhere, you have to fill the hydrogens to complete their valency. So carbon valency is 4. You have to, based on the carbon valency, you have to take the number of hydrogen atoms. So that is how we can write the structure of this alkene. Any doubt here? So write it complete structural formula and give IUPAC name for this. Say we have to number or number it from say 1, 2, 3. Why not 1, 2, 3. This is wrong. Why? Because this is the substituent which must get minimum position. So therefore, numbering should be done, and carbon atoms, depending on the number of hydrogens, you have to write hexa 1, 3, 5 triene, 3 methyl hexa 1, 3, 5 triene is the IUPAC nomenclature and complete structural formula for this. Now quickly we can go to the preparation of alkenes. So how we can prepare alkenes? So alkenes can be prepared from either catalytic hydrogenation of alkynes. So alkynes on partial reduction. So in the yesterday's session, we have seen when we take alkynes, let us take C triple bond C like this. Now, if I do hydrogenation, yesterday I told 2 moles of hydrogen in presence of platinum, palladium or nickel. 2 moles of hydrogen if I use, I can just get what? C single bond C like this, all replaced with hydrogens. Now I can get alkane here. Now if I take one by stepwise here, C triple bond C plus 1 mole of H2 if I add, now it becomes C double bond C, C double bond C with 1 hydrogen added. Further, if I add 1 more mole of hydrogen, then I can get the C single bond C and hydrogens, 2 moles of hydrogens are added like this. This is the hydrocarbon we are going to get. Now, if I want to stop the reaction here itself to get the alkene, so that is how we can prepare alkyne. Using alkyne, how I can prepare alkene. So I have to stop the reaction of this hydrogenation process here itself. So for that, what we do is partial reduction in with hydrogen, partial reduction. This is complete reduction. From here to here, it is complete reduction. From here to here, it is partial reduction. So we have to use a catalyst called as Lindlar's catalyst. What is this Lindlar's catalyst? Lindlar's catalyst is nothing but palladium in presence of charcoal and quinoline. Quinoline. This is the compound which is used to poison this catalyst. So palladium is highly active catalyst. So I want to decrease the activity of palladium. How I can decrease the activity of palladium? By adding the catalytic poisons. So we are going to add the catalytic poison over here, and charcoal is added to this palladium so that the activity of palladium is slightly decreased during the process and the reaction can be stopped at the alkene itself. That is one very important point to be noted. So either we can add palladium charcoal, palladium calcium carbonate, palladium barium sulfate, palladium charcoal. So these are the different combinations we can do that is all those combinations are called as Lindlar's catalyst. So Lindlar's catalyst is used for hydrogenation, one of the catalysts used here. So if we use Lindlar's catalyst and do the hydrogenation, hydrogen gets added and it is going to stop. Triple bond becomes what? Double bond. So now the question arises, if at all the compound to be formed is having a geometrical isomer, very important point to be noted here. If it is having a geometrical isomer, so then geometrical isomer must be cis isomer we are going to get in this particular catalytic hydrogenation. Say if we take CH3, C triple bond C, CH3. If I take this alkyne and do this hydrogenation in presence of Lindlar's catalyst, means palladium barium sulfate, quinoline, or palladium charcoal quinoline. So Lindlar's catalyst if I use, so I'm going to get the alkene which is CH3 on same side, HH on same side. This is nothing but cis alkene. If at all we get geometrical isomer, we are going to get cis alkene. If we are not getting the geometrical isomer, if I have a alkyne like a CH3C triple bond CH2, like this if I have, and if I do hydrogenation, it is not giving any cis or trans. It is giving the normal alkene because it does not exhibit cis or trans. C triple bond CH, not CH2, it is CH. So one hydrogen adds here, another hydrogen adds here. So the product is not having any cis or trans isomer, it will have normal alkene you are going to get. But if the product can be geometrical isomer, the type of geometrical isomer you are going to obtain here is only cis, no trans. Cis alkene you are going to get. So if you want to get trans, you need to use some other reagent. What is that reagent is? Trans alkene are obtained by sodium in liquid ammonia if you use. Sodium in liquid ammonia, if you use, you will get the trans isomer instead of cis isomer. So very, very important. You have to remember this particular reagent. Same hydrogenation, but in presence of sodium in liquid ammonia. That is what we are going to get, trans alkene. So this is, both reactions are catalytic hydrogenations only. One is Linder's catalyst, another is sodium in liquid ammonia. So these two will give you, if at all the alkene is having any of the geometrical isomer, Linder's catalyst will give you cis isomer, sodium in liquid ammonia will give you trans isomer. So very important point to be noted over here. So now another method of preparation is from dehydrohalogenation. So dehydro means, the name itself is self-explanatory over here. D means removal, hydro means hydrogen, and halogen. So simultaneously hydrogen and halogen are going to be removed during this process. Say what happens here is, we are going to use a reagent called alcoholic KOH. What do you mean by this alcoholic KOH? KOH. So KOH is dissolved in alcohol. It is called alcoholic KOH. Alcohol may be C2H1OH or CH3OH. So if you dissolve in alcohol, the reagent, what we call it as alcoholic KOH. So this alcoholic KOH is called as dehydrohalogenating agent. It is called dehydrohalogenating agent. So this alcoholic KOH removes, say, this OH of alcoholic KOH and H of this alkyl halide. So is been removed. Now one more point to be remembered. This is the functional group for us. The carbon atom which is attached to the functional group is called alpha carbon atom. And the next carbon atom is called beta. So the carbon atom which is attached to the functional group is called as alpha. The next carbon atom is beta. And hydrogen is eliminated from beta carbon atom. Therefore, the reaction is called beta elimination reaction. Beta elimination reaction. This is called beta elimination. So water is being removed and K will combine with X, forming KX. And now single bond becomes double bond because this bond has been broken. This bond has been broken. Now carbon cannot have 4 bonds if I break one bond, right? So this carbon also cannot have 4 bonds if one bond. So there is a carbon-carbon double bond is established between the two carbon atoms. So hence alkene is the product we are going to get in this very important reaction, dehydrohalogenation. So dehydrohalogenation. Example you can consider here this. CH3CH2Cn. CH3CH2Cn. I just erase all these things. You can just observe the reaction here. So next, this one, CH2 double bond CH2, ethene. This is been removed. This part is removed. So CH3, CH2 double bond CH2. Now, one more thing what you need to understand in this is, if we have a situation like this example called as secondary butyl bromide, common name, or 2-bromobutane. So this is the alpha carbon atom and we have two types of beta carbon atoms here. This is also beta, this is also beta. Now, if two different types of beta carbon atoms are there, then hydrogen is removed from which carbon atom? There are two possibilities, right? Two possibilities. One is hydrogen can be removed from this carbon atom, hydrogen can be removed from this carbon atom. So which hydrogen is removed and which is the major product? So for deciding the major product, we are going to consider here one rule called as Saytzeff rule. So we call it as Saytzeff rule. Sedgwick rule. So what this Sedgwick rule says? Sedgwick rule says that during this dehydrohalogenation, the major product is that product which has more number of alkyl groups on either side of the carbon-carbon double bond. So what do you mean by that? Say when I remove from this carbon atom hydrogen, I'm getting this product. Now, if you take double bond here, around this double bond, we have one methyl group and one methyl group this side. Either side, we have two alkyl groups. But if you take this double bond, we have only one ethyl group on this side, and this side we don't have any alkyl groups. So where we have more number of alkyl groups? We have more number of alkyl groups here. Therefore, this is the major product. So we have like this. So this is the major product. This is the minor product. So more number of alkyl groups where you are finding, that is the major product. This is called as Sedgwick rule. The number of when during this dehydrohalogenation, the major product is that product where the more number of alkyl groups are there in the around the carbon-carbon double bond. So that is called Sedgwick rule. Very many questions will be asked on this Sedgwick rule. The major product you must be able to identify, because this major product is more stable than this minor product. Why this is more stable? You can observe here. This in alkenes, you must have learned about hyperconjugation. So these three hydrogens can involve in hyperconjugation with this pi electrons of carbon-carbon double bond. Total 6 hydrogen atoms are there. Here only total 2 hydrogen atoms, because only these hydrogens can involve in hyperconjugation. And here this does not have any carbon atom attached this side. So here there is no hyperconjugation, only these two hydrogens. More the number of hyperconjugated structures, more is the stability of the compound. So that is very important to be noted. So therefore, the major product is more alkylated product is the major product in this case. So therefore, we get alkenes like this. Another method of preparation is from vicinal dihalides. What do you mean by vicinal? Means if the dihalide means two halogens present in the same molecule. Say we have halogens attached to the side-by-side carbon atoms, we call it as vicinal dihalides. So we use the reducing agent called zinc over here. So zinc in alcohol we use. This is going to remove both of these halogens attached to the adjacent carbon atoms, and we are going to get double bond between the carbon atoms forming alkene. So vicinal dihalides can be converted into alkenes using zinc in alcohol by heating it with zinc in alcohol. Zinc acts as a reducing agent over here, which is going to remove the more electronegative halogens during this process. So dehydration is another method. So dehydration is another method of preparing this alkene. Dehydration in the sense from alcohol. So alcohol, you know, OH group must be there. And if we have hydrogen attached to the alpha carbon atom, sorry, beta carbon atom, it is alpha now, and this is beta. So beta carbon atom, if you can remove hydrogen, these two will combine and you can remove the whole thing as water. Therefore, we call it as dehydration, where removal of water. Dehydration means removal of water. So dehydrating agent we need to use. What is the dehydrating agent here? 95% of sulfuric acid can act as dehydrating agent. If you pass the vapors of alcohol through alumina, that also is dehydrating agent. So temperature to be maintained, you must remember 443 Kelvin in this temperature, in this case, and 623 Kelvin in this case. So water is being removed during the process, forming carbon-carbon double bond. So this is also one of the methods of preparation of alkenes. Here, this is dehydration process. So these are the different methods of preparation of alkenes. Any doubt you have in the methods of preparation? Any of the methods of preparation? Any doubt? Shall we go ahead further? So now coming to physical properties, quickly we can go through first three members in the limit. You can, if you take the state in which they exist, the first three members are gases, next 14 members are liquids, and higher ones are solids. Ethene is colorless gas with slightly faint sweet smell. All other alkenes are colorless and odorless. So these are also insoluble in water because these are also non-polar in nature, but fairly soluble in non-polar solvents like benzene and ether, right? So now with increase of size of alkyl group, boiling point increases. As you know, size larger the size, more is the boiling point. So again, branching will decrease the boiling point. As usual, straight chain alkenes are having more boiling point than branched chain alkenes. Now let us discuss very important chemical properties of this alkenes. So one of the major reaction which alkenes undergo is addition reaction. So why this reaction, why this alkenes undergo addition reaction means because, as I told already, C double bond C, this will, this is electron rich and wants to get converted into unsaturated, from unsaturated to saturated. So if I want to make it unsaturated to saturated, this bond has to be converted into single bond. So this bond, single bond, if I want to convert, I have to make this, I have to remove this bond and make another bond to these two. So therefore, something gets added to both the carbon atoms. So they undergo addition reaction. So we are going to add something around the carbon-carbon double bond, or the carbon to those carbon atoms which are doubly bonded. So something is adding there. So therefore we call addition reaction. So addition, we are going to add to the carbon-carbon double bond to make it from, to convert it from unsaturated to saturated. So one of the addition we can do is dihydrogen. So we can add dihydrogen to carbon-carbon double bond. So when I add dihydrogen, I'll remove this and add hydrogen. That becomes alkane. Already we have seen the preparation of alkane here. The same thing in the presence of nickel, platinum, or palladium. So we can convert alkenes into alkanes. That is dihydrogen. Addition of dihydrogen. Already we have seen in the preparation of alkenes. Now coming to halogens. One more very important addition reaction is addition of halogens. Say if I take a C double bond C and add some X2 to this, X2 is halogen, you know, either maybe F2Cl2 Br2 or I2. So you can add this to this. What we can get is carbon-carbon double bond becomes single bond, and X gets added here, X gets added here. We are going to get vicinal dihalides. That is very important. Vicinal dihalides we can get here. So this is the reaction which undergoes addition of halogen to the carbon-carbon double bond. But one important reaction is with respect to bromine in carbon tetrachloride here. That is the important reaction. So the general reaction is this, as I already have written here. This is the general reaction. So if I take bromine in carbon tetrachloride here, bromine actually is reddish brown color. So reddish brown color it has. Now, in carbon tetrachloride, it has reddish brown color. Now, when I make an alkene to react, this is an unsaturated compound. So, when I make this alkene to react with bromine in carbon tetrachloride, bromine gets added to the carbon-carbon double bond. Now, when bromine gets added to the carbon-carbon double bond, this reddish brown color is now going to become colorless because all bromine gets added to carbon-carbon double bond. So the color of the bromine gets discharged. You can say it becomes now colorless. So reddish brown color becomes colorless because both bromine now added here. Here one bromine is added. Here one bromine is added. So when it becomes colorless, we can use this particular reagent, that is bromine in carbon tetrachloride, can be used. Where we can use is, I will give you an organic compound and ask you to check whether it is saturated or unsaturated. Let us assume that I have given you an hydrocarbon. I'll tell you this is an hydrocarbon. Tell me whether it is saturated or unsaturated. Then you can use this test. You have to just add bromine in carbon tetrachloride to that compound. If you get the discharge of the color, means colorless, if it becomes colorless, then it is unsaturated, because unsaturated compound, bromine is getting added. But if it is not discharging the color, it is saturated hydrocarbon. That is very simple test you can do. Unsaturated in the sense, it is not necessarily alkene. That also you must keep in mind. It is not necessarily alkene. Alkynes also decolorize. this bromine in carbon tetrachloride. So bromine in carbon tetrachloride can also be decolorized by any unsaturated hydrocarbon like alkenes or alkynes. So therefore, you can only say that it is unsaturated. Again, further we can have the other reactions for unsaturation also. Whether it is alkyne or alkene or alkyne, to get that other reactions also we can see. This is very important. Addition of hydrogen halides, formation of alkyl halide. Say when carbon-carbon double bond is there, if I add HX to this, hydrogen will add to one of the carbon atom, halogen will add to one of the carbon atoms. We call it as hydrohalogenation. Just now we have seen dehydrohalogenation. It is addition of HX. H and X gets added around carbon-carbon double bond. So we get what here is the product like this. H and X we are going to get. The name of this compound is alkyl halide. So we are going to get haloalkanes, or haloalkane is the common general IUPAC name. Alkyl halide is a common name. So we are going to get this as the product. Now, under this, we are going to learn in two cases. One is when we add HX to symmetrical alkenes, when we add HX to unsymmetrical alkenes. Two conditions we have to learn here. So first is symmetrical alkene. Let us take. If symmetrical alkene is there, you can add H and Cl anywhere you want. Any doubly bonded carbon atom, you can add this. You will get one product. So in this case, chloroethane or ethyl chloride, we are going to get. Ethene is a symmetrical alkene. So when symmetrical alkene is there, you can add hydrogen to any of the carbon atom. You can add Cl to any of the carbon atom. The product is same. There is no change in the product. So you will get, even if you add hydrogen to here or chlorine here, then also it is ethyl chloride. Same compound you are going to get. Symmetrical alkene, there is no problem. Wherever you want, you can add. This is also symmetrical. You can see but2ene. This is also symmetrical. This side and this side we have same. So HBr, when you add, you can add anywhere around carbon-carbon double bond. You will get the same product called as 2-bromobutane. So this is when you add symmetrical alkene is added with the HX, HCl, HBr, HI, anything you can add over here. Now, order of reactivity with respect to HI, which is going to add faster, you must remember. So HI adds faster than HBr than HCl. Why HI? Why not HCl or HF? It is much less greater than HF now. So why HF is not adding even though F is more electronegative? You can ask here. So here in this case, we are not worried about electronegativity here. We are worried about the bond strength. HI bond strength is weakest because iodine size is very large. As you move down the group, size of the halogen goes on increasing, bond length increases, bond strength decreases. Therefore, HI can easily be added to alkenes compared to HBr, compared to HCl, and compared to HF. This is the order of reactivity with respect to HX. Very important point to be noted this. Now coming to another situation, unsymmetrical alkene. Let us take this example. Propene is an example. So in this unsymmetrical alkene case, where you can add the hydrogen bromide, let me take. So where you can add, there are two possibilities over here. What are the two possibilities? Like this one possibility. Hydrogen adds to the second carbon atom, hydrogen adds to first carbon atom, bromine is adding to second carbon atom. This is one possibility. Another possibility is hydrogen adding to second carbon atom, bromine is adding to first carbon atom. So both of these possibilities, if you look into, now you can see there are two possible products. One is 2-bromobutane, and another is 1-bromopropane. So now how to decide which is the major product, or both we are getting 50-50% or what? So how we can decide here is, again, we have to follow one of the rules called as Markovnikov's addition rule. So what this Markovnikov's addition rule says, whenever you are adding an unsymmetrical molecule to an unsymmetrical alkene, the negative part will add to that carbon atom which has a less number of hydrogens. Now you can see carbon-carbon double bond. This has 2 hydrogens. This has 1 hydrogen. Now negative part will add to the carbon atom which has less number of hydrogen, and positive part will add to that carbon atom which has more number of hydrogen. Very simple way you can understand this. So positive part actually is hydrogen. So hydrogen will add to the carbon atom which has more number of hydrogen. Simple way you can understand this. Hydrogen is a positive part, and that positive part will add to that carbon atom which has more number of hydrogens. And the negative part will add to that carbon atom which has less number of hydrogen. We call it as Markovnikov's addition rule. When an unsymmetrical alkene reacts with unsymmetrical reagent, the negative part of the reagent gets added to the carbon atom containing less number of hydrogen across the carbon-carbon double bond. So this is called as Markovnikov's addition rule. So based on this Markovnikov's addition rule, so the main product what we are getting here is this 2-bromopropane is the major product. We are no doubt we are going to get the other product also, but it is minor product. So what is the reason for having the major product like this, and why this rule came into existence? So let us take with mechanism over here. So here first what is going to form is electrophile. We call this as electrophilic addition reaction. Because why we call it as electrophilic addition reaction? Because first electrophile gets added over here. So H plus is the electrophile. Br minus is the nucleophile here. So first what happens in the reaction? H plus attacks here. There are two possibilities. Let us write both the possibilities here. So first possibility is this. When H plus attacks this one, our electrons will get shifted over here. Then this becomes negative charge, and this will take this H plus, because H plus is positive charge. This center becomes electron rich, and this electron rich center now takes up this H plus. So now double bond becomes single bond, because both the electrons, so this is having 2 electrons, and 1 electron actually belongs to this carbon atom. But now both the electrons have gone here. That means this carbon atom will get positive charge. And here there is a single bond established. So we get like this. This is an intermediate we are getting. So intermediate, we are getting an intermediate. Similarly, we are getting an intermediate like this. In this case, if the second case, this is the intermediate obtained, CH2 plus. Now, as I told, free radical case and carbocation cases are same. What do you meant by carbocation? You must have learned in first chapter. The carbon bearing the positive charge is called carbocation. So here we get the secondary carbocation. So what is secondary carbocation? The carbon which is having a positive charge is attached to 2 other carbon atoms is called secondary. The carbon atom having a positive charge, if it is attached to only one other carbon, is called primary. So which is more stable? I told in case of free radical, similar here, same with respect to carbocation. Free radical stability, carbocation stability is same, order is same. The reaction intermediate stability's order is same. Tertiary carbocation is more stable than secondary carbocation, is more stable than primary carbocation. So this is how we can take this reaction for the secondary, tertiary, secondary, and primary. So therefore, more intermediate what we are getting here as a result of addition of H plus, secondary carbocation is more stable, and this secondary carbocation is now added with Br minus to get 2-bromopropane as the major product. So this reaction is now faster than that reaction. See, if you have, say, CH3, CH2, CH2 plus Br minus. Now there also there happens, but this happens slowly. Therefore, more amount of this is going to be formed. Therefore, major product is this. CH3, CH2, CH2, Br. Here it is 2-bromopropane, there it is 1-bromopropane. So therefore, we can get the major product as this. Any doubt in this? Everyone understood? Very important point. So one more condition we have, anti-Markovnikov's addition. So what is this meant by anti-Markovnikov's addition or anti-Markovnikov's addition? This is opposite to Markovnikov's rule. Under what condition we can get the product? Opposite to Markovnikov's addition. So under this condition, HBr peroxide. So if I take an alkene like this, if it is an unsymmetrical alkene, not symmetrical, symmetrical it doesn't apply. Only it is applicable for unsymmetrical. HBr peroxide, if I take like this, then it will follow anti-Markovnikov's addition. So if I'm getting 2 bromopropane means 1 bromopropane is the major product here, not 2 bromopropane. Only in this condition, HBr peroxide. Not even HCl peroxide or HI peroxide. In these two cases also, it is not true. It is true only with respect to HBr peroxide. And this effect is called as Kharash effect. The scientist who found this anti-Markovnikov's addition. Kharash effect, peroxide effect, anti-Markovnikov's rule. So let us take an example of this Kharash effect or anti-Markovnikov's rule here. The same propene I have taken, unsymmetrical alkene, HBr, peroxide. In presence of peroxide, you will get the major product as 1 bromopropane, not the major product as 2 bromopropane. If you have this peroxide effect is like that. So how this peroxide affects this? So let us examine this with the mechanism. So what is the mechanism behind this? So we have first, this say benzoyl peroxide. So this is called benzoyl group, C6H5COO, C6H5CO. So this is CO, not COO. This is called benzoyl group. Benzoyl peroxide. You know, hydrogen peroxide like this, HOOH will be there. Both H's are replaced by benzoyl group, that is C6H5CO. So peroxide, what happens here in this is, this benzoyl peroxide undergo homolysis. That means this oxygen-oxygen bond, there is 1 electron here, 1 electron here, both are equally distributed. So when these are equally distributed among the oxygens, the oxygen will now get 1 unpaired electrons. So there are 2 molecules of such benzoyl free radicals. We call them as benzoyl free radical. Now this benzoyl free radical gives away its electron, and now this will undergo homolytic cleavage. You can see this will undergo homolytic cleavage, and that electron shares with this, and you are going to get phenyl free radical as the intermediate over here. So carbon dioxide will go like this. This will go as carbon dioxide, phenyl free radical you are going to get. Now this phenyl free radical, this is chain initiation. This is free radical mechanism, means chain gets initiated. How the chain gets initiated is by forming the phenyl free radical. So this phenyl free radical further reacts with HBr. HBr undergo homolytic cleavage now, and Br free radical you are going to get. And this 1 unpaired electron on carbon, 1 unpaired electron on hydrogen will combine to give benzene as the byproduct here. And Br free radical is going to be formed. Now this, what is the next thing? This is chain initiation. Once the bromine free radicals are formed, this bromine free radical will react with alkene now. So this bromine free radical now has 2 options like this. It can add in 2 ways like this. One way is like this, another way is like this. It can add to first carbon atom, it can add to second carbon atom, 2 possibilities. Now after adding to the first carbon atom, we are getting the secondary free radical here, right? This is secondary free radical. Now this is the dot, what we have is primary free radical. So which is more stable again? Again, secondary free radical is more stable. Therefore, the hydrogen now has to be the hydrogen H dot now has to add to this to get the stable compound. So the last step is, what is the final formation of the product? So H gets added to the second carbon atom, so that we get 1 bromopropane as the major product over here. So this is how we explain why we are getting the major product as 1 bromopropane in the hydrogen peroxide case. Now, coming to one more question here. Why not it is possible for HCl peroxide? HCl plus peroxide. Why not it is possible? Why not it is possible for HI peroxide? Only why it is for HBr peroxide? Why? Because here, if I go back in this slide, if I go back, the formation of bromine free radical. So bromine free radical is formed in the first step, correct? Now phenyl free radical is inducing this particular reaction, free radical, formation of bromine free radical. If it is HCl over here, phenyl free radical cannot break this bond. Why? Because HCl bond is very strong compared to HBr. The bond strength is very high because of smaller size. Cl is smaller than Br. So HCl bond strength is much higher than HBr bond strength, and hence phenyl free radical cannot cleave HCl bond homolytically, forming chlorine free radical. It cannot form chlorine free radical so easily. That's why it is not going to be observed peroxide effect in case of HCl. Now, in case of HI, if I take HI case, step 2 is not possible. Why not step 2 is possible in HI case? HI, you can ask, HI is weaker bond, then it could have undergone. Yes, HI is weaker bond. Once it forms H dot and I dot, after homolytic cleavage with C6H5 dot, no doubt it is going to form benzene. Now, I dot and another I dot, they combine together forming iodine over here, which is more stable. Iodine is going to be formed and iodine is more stable over here. Therefore, we cannot have peroxide effect for HCl and HI. Only it is applicable to HBr in presence of peroxide. Understood all of you? Any doubt? So this is very important point to be noted over here. So anti-Markovnikov's rules are only applicable for hydrogen, HBr peroxide and sunlight only. Markovnikov's and anti-Markovnikov's rules are only applicable for unsymmetrical alkene. I told you, symmetrical alkene doesn't matter. The product is same. Symmetrical alkene, it doesn't matter. The products are same. Okay. So now I hope we can conclude today's session by this reaction. We can continue to the next session about this hydrocarbons. Is that okay? Any doubts you have in the today's session? Yes, students, are you there?
No doubt, sir.
Yes, understood the concepts over here.
Yes, sir.
Okay, very good. Yes, I hope, sir. Are you there, sir?
Yes, sir. Absolutely, sir.
Yes. Shall we conclude today's session, sir?
Sure, sir. Sure, sir. Students, please revise all the properties and all the reactions, preparations and properties. All these are chemical reactions. You have to write every reaction and see. Okay. So then that is when you'll become very strong in them. So please follow that. And I request, sir, these slides also can be shared.
Yes,
so
after completing this chapter, I'll share this slides.
Sure, sir. So meanwhile, students, please take your textbooks and do all these equations and all the points sir has mentioned. Please go through them, revise them today itself. Thank you, sir.
Thank you, sir.
Okay, students, with that, we conclude our session. Now, you know the schedule. So Monday, we have our exam. And Tuesday, once again, I have requested sir to take it. I think Tuesday, does it work for you, sir?
Yes, sir. I can take on Tuesday.
Yes, sir. So Tuesday, we will be having the next class again at the same time from 5:30 to 7. Okay, students, all the best. See you all on Monday. Bye.